Picture this. A single container ship the size of 4 football fields, stacked with thousands of steel boxes weighing tens of thousands of tons, somehow floating on water like a bathtub toy. It defies common sense. Steel is heavy. Steel sinks. So how does something that massive not just plunge straight to the ocean floor? The answer isn't magic. It's one of the oldest and most elegant principles in physics, discovered over 2,000 years ago by a man sitting in a bathtub. Let's start with what seems obvious. If you drop a solid steel ball into water, it sinks immediately. Steel is about 8 times denser than water, so logically a ship made of steel should sink too, right? But here's the trick. A container ship isn't a solid block of steel. It's hollow, and that changes everything. When you place an object in water, it pushes the water out of the way. The water pushes back with an upward force called buoyancy. The amount of that upward push depends on how much water the object displaces, not how heavy the object is. Think of it this way. Imagine you fill a bathtub completely to the brim. Now slowly lower a bucket into the water. As the bucket sinks, water spills over the edge. The weight of that spilled water is the exact amount of upward force the water is giving the bucket. This is Archimedes' principle. Any object submerged in water experiences an upward force equal to the weight of the water it displaces. If the object weighs less than the water it pushes aside, it floats. If it weighs more, it sinks. So even though a container ship is made of heavy steel, it's shaped like a giant hollow bowl. The hull stretches deep into the water, pushing aside an enormous volume. And because water is heavy, 1 cubic meter weighs about a ton. The ship displaces thousands and thousands of tons of water. As long as the total weight of the ship, the steel, the cargo, the fuel, the crew, everything is less than the weight of the water it displaces, the ship floats. But there's more to it than just floating. A container ship doesn't just sit there. It has to stay stable, even when waves hit it, even when cargo shifts, even when it's loaded unevenly. This is where the design gets clever. The hull is shaped to sit low in the water. The heavy cargo is stacked on top, which sounds dangerous, but engineers balance it carefully. They calculate something called the center of gravity, the average point where all the ship's weight is concentrated. At the same time, the water pushing up on the hull creates an upward force at a point called the center of buoyancy. For the ship to stay stable, the center of buoyancy has to be positioned just right relative to the center of gravity. If the ship tilts to one side, the underwater shape of the hull changes. More of the hull dips into the water on the tilted side, which means more water is displaced on that side. The buoyant force shifts, creating a correcting push that tries to level the ship back out. It's like a self-balancing system built into the shape itself. Now here's where it gets even more impressive. A fully loaded container ship can carry over 200,000 tons of cargo. That's the weight of about 40,000 elephants, and yet it only sinks a few extra meters deeper into the water. Why? Because the hull is so large that even a massive amount of added weight only requires displacing a bit more water. The ship settles lower, pushes more water aside, and the buoyant force increases just enough to hold the extra load. Engineers measure this with something called the Plimsoll line, a marking on the side of the hull that shows how deep the ship can safely sit in the water. Load it past that line, and you risk sinking. But as long as the ship stays within that limit, the physics holds. The water keeps pushing up with exactly the right amount of force. So in the end, a container ship floats for the same reason an empty bottle floats. It's not about the material, it's about the space inside. The hollow shape lets the ship displace far more water than a solid chunk of steel ever could. And because water is heavy, that displaced water pushes back with enough force to lift thousands of tons of cargo across entire oceans. It's simple. It's ancient physics. And it's the reason global trade even exists.